Hello, dear students. Hope you all are doing well. In our previous session, we have already discussed the case of motion in a straight line. Under motion in a straight line, we have discussed the concept of distance, displacement, speed, velocity, acceleration, uniform motion, non-uniform motion, motion in a straight line under constant acceleration, and we have taken the case of motion under gravity. So, after all these discussions, in this session, we will discuss the concept of graph. So, how can we represent motion in a graph? And we have different cases of graph like displacement versus time graph, right? Velocity versus time graph, and acceleration versus time graph. So, in all these three type of graphs, we will extend our discussion, right? So, let's start. Yes, so our discussion is basically graphical analysis. So under graphical analysis, we have a few variables in motion in straight line, and these variables are displacement, velocity, acceleration, and time. So we will see the case of displacement versus time graph, velocity versus time graph, and acceleration versus time graph, right? So this is what? This is displacement versus time. Second one is velocity versus time. And acceleration versus time. Right? So few things we have to be very clear that under displacement versus time graph, we will have few things like the slope of displacement versus time graph. So in a displacement versus time graph, slope gives the velocity, right? And you can also have the concept of area under displacement versus time graph, right? So here area, we will not discuss area in case of displacement versus time graph. In case of velocity versus time graph, again, you will have slope as well as area. So regarding slope, velocity versus time graph, slope gives you acceleration. And area of velocity versus time graph, so area under VT graph gives you displacement. Right? Again, the concept of acceleration versus time graph. So in case of acceleration versus time graph, you will have slope as well as area under AT graph. So in case of graph, we will not discuss the slope, we will discuss the area. So area under acceleration versus time graph gives you velocity. Right? So what are the important things you have to consider? Slope as well as area. So let's start with the concept of displacement versus time graph. So displacement versus time graph, or you can write it as ST graph. ST graph, basically it it is a graph between displacement and time. Suppose initially an object is having some position, and with respect to time, what condition we can have that object is not moving, right? And since object is not moving, it is having its position is at the origin, right? So let's see all the cases. So in the y-axis, I am taking displacement, and in the x-axis, I am taking time. So in all the cases, actually time will continuously pass down, or you can say time is always increasing. But distance or position, we can't say that distance is increasing or position is changing until unless the object is not moving, right? So see, suppose I am considering the case that object is stationary. Object is stationary means object is not moving. And suppose I'm considering its initial position at some position like this is x is equal to 0. This one is x is equal to 5, right? So its initial position, you can say it at x is equal to 0, at time is equal to 0, right? So initially, the object is at x is equal to 0, at time is equal to 0. If I'm saying that object is at the same position, it is not moving. Since I'm considering that object is not moving, you mean that its position will always be at x is equal to 0, but time is changing, right? So at t is equal to 0, its position is at o, but after some time its time will increase, right? So time will increase, but position will not change. So its graph will be along the x-axis, and time is increasing, but position is not changing. Suppose I'm considering that its initial position at x is equal to 0, suppose its position at t is equal to 0 is at 5 5 meter, and at t is equal to 0. So at t is equal to 0, its position is at 1, 2, 3, 4, and this is 5, right? 5, you can say it is in meter, so displacement is in meter. So its position 5 meter and object is stationary. That means always its position will be at x is equal to 5 meter, but time is increasing. So the graph will be a straight line, right? So in this particular case, you can observe that the slope of this graph is actually 0. Slope is 0 means its velocity is 0. Since object is stationary, so in that case, its velocity will be 0, right? Now, let's consider the case when object is not moving. Yeah, actually, let's say one more case, the VT graph. In the same case, when object is stationary, VT graph. So for VT graph, so in case of VT graph, as we know, velocity is 0. So when object is stationary, then graph will always along the x-axis, right? So this is a graph when object is stationary, right? Let's see the case when object is moving, right? So when object is moving, so object can move with uniform velocity. So uniform velocity means actually velocity is constant throughout the motion, right? Since velocity is constant, what we can observe in displacement time graph, so in case of ST graph, suppose initially the position of an object it at x is equal to x naught. So this is actually the position. What I'm saying, this is a position, x naught is initial position. So initial position is x naught. Since object is moving with uniform velocity, so in this case, since velocity is constant, we can say that the graph will be a straight line, right? So here graph will be a straight line making some angle with the horizontal. So here the graph is making some angle with the horizontal, and that angle is theta, right? So this angle is theta, and its final position is suppose after some time xt. So after some time, since its position is changing, we can say that after some time t, its position is now xt. So how can you find out the slope? For any graph, the slope is actually the tan theta. Suppose you have any graph between x and y axis, then the line, any line making some angle theta with the horizontal. So tan theta is actually the slope of this graph. So here in this particular case, tan theta will be, I'm saying this point is A and end point is B and this point is C. So tan theta here will be slope, and tan theta will be actually equal to perpendicular upon base, means it is equal to BC upon AC. And from the graph, you can see that BC is xt minus x naught and AC is time t. So this will be xt minus x naught divided by t time t. And xt minus x naught is what? Actually, this is the displacement divided by time. So slope is nothing but displacement upon time, and it gives you the value of velocity. So in case when the object is moving with the uniform velocity, in that particular case, the slope of the graph gives you the value of velocity, right? So in xt graph, velocity with uniform velocity, we have considered uniform velocity, that means v is equal to constant. In the same case, if we have to draw the graph between velocity versus time, so for vt graph, So here, as velocity is constant, v is constant, that means slope of the displacement and time graph is constant. So velocity is having the constant value. That means the value of velocity will not change throughout the motion. So here v will be constant, right? Velocity is not here zero. Velocity is having some value. So suppose velocity is having value v, and the graph will be vt graph, right? Getting my point? So this is the case when object is moving with uniform velocity. We are not considering here the case of acceleration. The concept of acceleration we will discuss after displacement time graph and velocity time graph, right? Now let's consider that initial position of an object is at some position. We can say that x is equal to x naught, right? This is x is equal to 0. And if its position is now, it is coming to the negative direction. Suppose now its position is x is equal to xt. Now it is coming to the negative direction, means it is coming to the origin. How can you draw the graph of displacement versus time? So after time t, so this position at t is equal to t and x is equal to 0 is at t is equal to 0. So for drawing this kind of graph, actually you have to take xy axis. So position versus time graph. And here initial position is x naught and final position is after t time somewhere here xt. So in this case, again you have to draw the line. Now you have to find out the velocity. So in this particular case, you will find that if you find out the slope of this line, so the slope of this line will be actually making obtuse angle. And since it is making some obtuse angle, that means slope will be negative. Since slope is negative, we can say that now velocity is in the opposite direction, right? So velocity is in the opposite direction. That means it is making obtuse angle or negative slope with the x-axis, right? Now come to the case of acceleration versus time graph. So let's consider the case of uniformly accelerated motion. So under a uniformly accelerated motion, we can have again ST graph and VT graph, also AT graph. So for ST graph, suppose in case of uniformly accelerated motion, what you say that its position is actually changing, right? So since there is an acceleration, you can say that velocity is not constant. Velocity is not constant, and velocity is either increasing or velocity is decreasing, right? So if I'm saying that initial velocity is zero and final velocity is having some value, and position at t is equal to 0, its position is somewhere s is equal to 0, right? So since initially the position is at s is equal to 0, at t is equal to 0, and initial velocity also we are considering that u is equal to 0, and final velocity means at t is equal to t, velocity, final velocity is having value some v, right? So your graph will be either increasing or decreasing slope. It depends, your graph is either increasing or decreasing, depend on either it is accelerated or retarded, right? So let's first see the case of velocity time graph. So for velocity time graph, initial velocity at t is equal to 0, we have considered it as u is equal to 0. So initial velocity is this one, right? And final velocity, it is increasing, having some value here. So since this is a case of uniformly accelerated motion, so slope of VT graph gives you acceleration. So this line is making some angle with the horizontal, right? We are considering initial velocity is 0. So this angle theta, so here slope will be tan theta, and this tan theta is equal to perpendicular, means this is v divided by base, which is equal to time. So this will be v upon t. And we know that change in velocity per unit time is acceleration. So slope of VT graph gives you acceleration. Right? Since velocity, we have considered velocity is increasing, velocity is not decreasing. Since velocity is increasing, now ST graph, by considering equation of motion, we can find out S is equal to ut plus half at square. Initial velocity is 0 and having constant acceleration. Now we can say that S and T graph will be parabolic. So this graph will be something like this, right? So S is equal to half at square. This is your ST graph when velocity is increasing, and again position is having parabolic equation with the time, right? So this is a case of uniformly accelerated motion. Let's take one more case that suppose initial velocity is having some value. So initial velocity means at t is equal to 0, velocity is what? U. And final velocity means at t is equal to t, this is equal to having some value v, right? And uniform acceleration a. So let's draw the ST and VT graph. So this is VT and second one is ST, right? So initial velocity means at t is equal to 0, we have taken the case that initial velocity is u. So at t is equal to 0, initial velocity is u. But after some time t, its position is also changing and its velocity now is v, right? So the line joining initial and final velocity will be this one. As we have already seen that the slope of VT graphs gives you acceleration. So in this particular case, slope, this theta will be, suppose this point is A, B, C, and this point is M. So tan theta or slope will be equal to BC upon AC. From the diagram, it is very much clear that BC is V minus U and AC is time t. So this will be V minus U upon time t, right? We know that slope of the VT graphs gives you acceleration. So you can say that V minus U upon t is acceleration A. From this relation, you can see that V minus U is equal to AT, or V is equal to U plus AT. So this is a case of first equation of motion. This is how you can drive first equation of motion graphically, right? Again, we have seen that the slope of VT graph, right? Slope of VT graph gives you acceleration, and area under the VT graph gives you what? Area under the VT graph gives you displacement. So for the displacement concept, you have to find out the area under AB graph. So area under AB graph will be this area. So this whole area is actually area is equal to area of triangle ABC plus area of rectangle AC, M, and O. So area of triangle ABC, we know that it is 1 by 2 base into height. So here base is AC. Into height BC, right? Plus area of ACM, this is rectangle. So this is nothing but L into B. So here L is what? OM into AO. You can put the values here. So this is 1 by 2. AC is T and BC is V minus U. Plus OM is T and AO is U. So area is actually equal to displacement, which is S. Now you can say that S is equal to UT plus 1 by 2 V minus U into T. And from the first equation of motion, you can say that V minus U is equal to what? AT. So in the place of V minus U, we can write it as AT. So now it is AT into T, or you can write here as S is equal to UT plus half AT square. This is second equation of motion we have proved graphically. Hope you all are getting my point. For the third equation of motion, we have to take the same case, but we have to do some mathematical changes. So for the third equation of motion, again, we can use the same relation, that S is equal to, or area is equal to, S is equal to T by 2 into V minus U, and plus UT, right? So from this relation, actually, instead of T, from the first equation of motion, instead of T, you can write here as V minus U upon A. So you can put here as V minus U upon 2 into A. So this will be actually V minus U. We can write here as V minus U into T by 2 plus UT, and we can take actually T as a common. So when we take T as a common, so this T is common, or you can take T by 2 as a common. So finally you will have V minus U plus 2U, right? And this can also be written as T by 2 into V plus U. Fine. So S will be equal to V plus U into T by 2. And from the first equation of motion, we have already seen that T will be equal to V minus U upon A. So you can write here as V minus U upon 2A, or 2AS is equal to V plus U into V minus U. So you can use the relation A plus B into A minus B. This is equal to A square minus B square. So finally you will have V square minus U square is equal to 2AS. This is what? Third equation of motion. So by the use of graph, you can drive all these three equations of motion, that first, second, and third. For the first equation of motion, you have to use the concept of slope. So slope of VT graph gives you acceleration. For the second and third equation of motion, you have to use the relation that area under the graph is actually equal to displacement. So for the first part, when displacement will be equal to sum of the area of triangle plus sum of the area of the rectangle, and when you solve these two area equation, you will get the relation S is equal to UT plus half AT square. When you replace time from the first equation of motion, which is equal to T is equal to V minus U upon A, then you will get the relation V square minus U square is equal to 2AS. So this is what they required. And in the same case, if you have to draw the ST graph in that case, so for uniformly accelerated motion, for ST graph, so again, we can consider that either initial position is S is equal to 0. So since initial position is S is equal to 0, we can say that graph will be something like this. So S is equal to initial position. If I'm saying initial position is having some initial velocity, so this is equal to ut plus half at square, right? So initial position here we have considered as 0. But if initial position is having some values, for example, initial position is having value S is equal to S naught. Since initial position is S naught, the graph will be something like this, right? So graph will be S is equal to S naught plus ut plus half at square. You can use this relation. So this graph which we have discussed is actually the graph of uniformly accelerated motion. But in case of uniformly retarded motion, means acceleration is in the negative direction, then what can we do? So let's see the case. Uniformly retarded motion. So for uniformly retarded motion, suppose initial velocity is u and final velocity is v. So for VT graph, initial velocity I'm considering as v, and final velocity is actually can have different values. It can be either we can say that final velocity it is becoming 0, you can say. So initially any object is having some value and after some time it comes to the state of rest. So this will be your graph. Initial velocity is u, and after some time, you can say after time t, its velocity is becoming 0. So this is making actually negative slope. Since it is making negative slope, you can write here as v is equal to, this is a case of v is equal to u minus at, right? So slope is negative, slope is this one. Fine. And in the same case, if you have to draw the ST graph, so for this ST graph, so in this ST graph, your graph will be what? As we know that the slope of ST graph gives you velocity, right? So in case of retarded motion, what you can observe, velocity is increasing or velocity is decreasing. So actually, in case of retarded motion, velocity is decreasing with respect to time. So velocity is decreasing with respect to increase in the time. So here, slope of the ST graph will be decreasing slope, not increasing slope. So remember one thing, for any graph, if the tendency of the graph is to become horizontal or parallel to horizontal, in that case, you can say its slope is decreasing. But if the tendency of the graph is to become perpendicular like this, so its slope is increasing, right? So in this particular case, we have seen it's a uniformly retarded motion. So velocity will decrease. Since velocity is decreasing, that means ST graph will having tendency to become horizontal. So ST graph will be something like this. Getting my point? So here velocity is actually decreasing with respect to time. Hope this thing is clear to all of you. Now let's see one more case. The case of uniformly retarded, then accelerated in opposite direction. So uniformly retarded, then accelerated in opposite direction. So uniformly retarded means suppose initial velocity is u, right? And it is having some value 0 at time t is equal to 0. So at t is equal to t naught, velocity is equal to 0. And then again, it is increasing in the opposite direction. You can see the case like any ball. It is you can say any car moving with some velocity u, and after some time at reaching this position, x is equal to, you can say, x naught, its velocity is becoming 0, and then it is moving in the opposite direction. So you can draw the graph. So this is VT graph. So in case of VT graph, initial velocity is u, and with time at t is equal to 0, it is having some 0 value. So velocity here at value 0, and now it is moving in the opposite direction. And for the same case, if you want to draw the so for ST graph, again, so for ST graph at t is equal to 0, actually at t is equal to 0, what is having velocity is having 0 value. So graph will be something like this. So at t is equal to 0, it becomes horizontal, means slope is 0, means velocity here is 0. So these are the cases of graphical motion, or you can say how can you represent motion in a graph, and graph is ST, VT, and AT. So here I'm ending this session. Thanks for watching. All the best.